Welcome back to Statistics. If you've ever taken a standardized test like the SAT or the ACT, and there are other examples as well, your score may have been reported as a percentile. So, for instance, you may have found that on the SAT, your score was in the 88th percentile. What that means is that you did better or as well as 88% of the people who took the test. So today we're going to talk about percentiles as they relate to the normal distribution. We'll define them, see what they mean, and show how to calculate with them. So percentiles of a normal distribution. So the definition is that a percentile of a distribution is a value that has a prescribed left tail area. So for a normal distribution, you would look at a picture like this. So if the area prescribed is P, where P would be between 0 and 1, and X is the value that has that area in its left tail, then we would say that X is the Pth percentile of the distribution. And that just means that the area to the left of X is going to be equal to P. So let's see an example. Suppose that Jack finds out that his score on the math portion of the SAT is at the 91st percentile. What score did Jack make? Let's assume that the SAT math score is normally distributed with a mean of 500 and a standard deviation of 100. So we take a look at the relevant distribution, and as opposed to problems we've seen in the past, in this one, we're given the left tail area as 0.91. And what we need to find is the value x that has that left tail area. So we need to find the value of x such that the probability of all values represented by capital X there, less than or equal to little x, is equal to 91% or 0.91. So using technology, we can get the answer pretty quickly. Turns out that little x equals 634.08 is the value that has a left tail probability of precisely 0.91. So we would say that the 91st percentile of the SAT math scores occurs at a score of 634.08. So you might be interested in how we actually got that number. It just magically appeared on the slides again. It's pretty easily obtainable from SALT. So let's take a look there. So here I just popped up the distribution calculator for normal distributions. And the first thing we would do is get the normal distribution we're interested in. So that has mean 500 and standard deviation 100. And then percentiles are all about left tail areas. So let's select left tail over here in the calculator. And then you simply put in the answer box, in the box that gives you the probabilities, put in the percentile that we need. So we need 0.91, and then we read off the value here in the box. So that's where the 634.0755 comes from, and I rounded that in the slides to 634.08. So it's a straightforward matter in SALT to compute percentiles. Here's another example. Height in inches follows an approximate normal distribution with a mean of 68 inches and a standard deviation of 2.5 inches. How tall must a person be in order to be in the top 5% of this population in terms of height? So again, let's begin with a picture. I've drawn the normal distribution with mean 68 and standard deviation 2.5, and I've just kind of highlighted what I would guess would be the top 5%. So the top 5% would be a right tail. To convert that into a percentile, you just find the corresponding left tail, right? The left tail would be 95% because the left tail and the right tail together have to add up to 100%, right? So the percentile corresponding to the top 5% would be the 95th percentile. And we need to find the value of x, that's the upper bound of that left tail region. So again, we would go to SALT or some other calculating tool and find that value. Turns out to be 72.11 inches. So the 95th percentile of our height distribution is 72.11 inches. And therefore, the top 5% of the height distribution begins at 72.11 inches. Here's another example, this one a little bit different. How many standard deviations above the mean must an observation from a normal distribution be in order to be in the top 1% of all observations? So one thing that's different about this example is that it's not specified which particular normal distribution we're talking about. It just says, how many standard deviations must you be in any normal distribution to be in the top 1%? But that little phrase is really the key. When we're asking about how many standard deviations are required, that's really a question about z-scores, right? Because the z-score measures the number of standard deviations. And we know that the z-score follows a standard normal distribution. So this is really a question about the standard normal distribution. We want to know what value of z has a left tail area of 0.99, right? Because that would make the right tail the top 1%. So once you formulated the problem that way, you can just again use SALT or any other statistical calculator to find that value. And it turns out that the 99th percentile of the standard normal distribution, it has a boundary at z equal 2.3263. So that's where the top 1% would be. And so we would need to be at least 2.3263 standard deviations above the mean in order to make it into that top 1%. Once you have that kind of information, you can really answer a host of questions about normal distributions a lot more simply. So for instance, suppose IQ is normally distributed with a mean of 100 and a standard deviation of 15. What IQ is necessary to be in the top 1% of all individuals in terms of IQ? Well, we could do this just like we did examples 1 and 2, and that would work perfectly fine. But example 3 actually gives us a shortcut because it tells us that the top percent of any distribution begins at, or any normal distribution, begins at 2.3263 standard deviations above the mean. So what IQ would that correspond to? Well, it would be 100 plus 2.3263 times the standard deviation of 15. And that turns out to be 134.89, essentially 135. So we were able to do the problem with just simple arithmetic here once we know how many standard deviations it takes to be in the top 1%. So that's a quick introduction to percentiles. I hope you found this helpful. As usual, let me know if you have questions or comments, and we'll see you next time. Y'all take care.